Hello, everybody, and welcome back to Geography 340 Climatology. I am Dr. Zach Hilgendorf, and today we're going to be talking about global surface air temperatures. So this is building off of our last lecture on just surface air temperature in general. In this, we're going to look at kind of a broad outlook on what drives global surface air temperatures, what patterns, what trends drive that. We're going to touch on, I think, 6 of them. In future videos, we're going to dive into a few of those in particular, like ocean currents and gyres, and as well as atmospheric pressure cells. So we're going to talk about them in general in this video, and then we'll dive into them a little bit deeper in the future. So let's first off start out here and just look at the bulk. So surface air temperatures, we're going to focus on spatial annual patterns and controls. If you think back, we looked at kind of annual controls. So we looked at, or sorry, more temporal based, so diurnal and temporal based patterns. We talked about annual and seasonal patterns as well. We're going to throw space into that. And to get to that spatial aspect, we need to go a little bit more global. So here we can see the average January surface air temperature, the map on the top in degrees Celsius versus the July surface air temperature map in degrees Celsius on the bottom left. So we can see a few different things here. We can see reference to the thermal equator on both of them. That's kind of that median temperature across the planet. That's not necessarily the latitudinal equator. We can see kind of lines going across all of these maps, kind of these gradational colors spectrums here. This is what we call isotherms. So we're looking at kind of cutoff points, if you will, between different air temperatures. And it doesn't surprise us, does it, where the bulk of the hottest temperatures are, right? Right, kind of along the equator for the most part, or the average air temperature is kind of right along the equator. Now, once we get up to the subtropics, around the Tropic of Capricorn and Tropic of Cancer, we see heightened air temperatures kind of infiltrating. We see kind of our desert, our arid environments as well, kind of poking out. We see our really, really polar and continental climates sticking out in northern Russia and in the northern portions of North America as well. We can also see that here. So this is also another similar figure, just looking at the average annual air temperature for these different regions. So what controls global surface air temperature patterns? Well, the first one, and the one that we should know by this point, I hope at least, is latitude, right? Where you are, your latitudinal position on our planet, drives the amount of insolation that you have. And if you are losing out on insolation or incoming solar radiation, you're losing out on that energy to drive that increase in surface heating, which drives the increase in long wave radiation emitted from the Earth, which drives temperature. Yeah, so temperature generally decreases with increasing latitude. Why? Well, for what we already said there, because insolation intensity generally decreases with increasing latitude. So latitude is the first easy picking one. Temperature is a great way to look at it. You can also say that annual temperature ranges generally increase with increasing latitude, if that makes sense. So our highs get higher, our lows get lower. The range increases, generally speaking, with increasing latitude. Why? Well, let's think about our solstices here for a second. So we've seen these renditions of Earth before. We noticed the equator, the Tropic of Cancer, 45, so our mid-latitude, and then 66.5 degrees north latitude, so our Arctic Circle. On the December solstice, right, we should know what we're looking at here. Along the equator, 12 hours of daylight, 1,248 watts per meter squared is our average insolation, 928, 499, and 0 up near the top. This is all review, right? Now, during the June solstice, 12 hours of daylight along the equator, 1361 watts per meter squared, and 13.5 hours of daylight along Tropic of Cancer. 1,266 watts per meter squared, 15.5 hours of daylight. And along the Arctic Circle there, 995 watts per meter squared, 24 hours of daylight along within the Arctic Circle. So we think of these variations in daylight and in insolation based off of our seasons. So that latitudinal difference is really important. And as you get further, we think of the Arctic Circle, for example, in December, sees no sunlight, right? The land of the midnight sun. But if you see it in the June solstice, it's getting 24 hours of daylight. And if you look at, our home, right, right around 45 degrees north latitude, we go from 499 watts per meter squared at 8.5 hours of daylight in the December solstice to 1,266 watts per meter squared at 15.5 hours of daylight during our June solstice. So we see these variations, and we did this in the total daily insolation random homework. We're kind of learning about how these fluctuations in latitude are so prevalent. So this one's not news to us, right? We knew about latitude. But we can look at areas here like Manaus during the January and July temperatures. So there, it's right along the equator. We're not seeing rapid or vast differences, right? It's located so central that seasonality isn't necessarily at play. If you go up to Dallas-Fort Worth, for example, if we look in the January one, we're actually getting down there. We get pretty cold. If we look there, our average looks to be around, it gets down to, 0 to 6 degrees Celsius. It can, average air temperature, so a little bit above freezing. Whereas in the summer, we're seeing that'd be 27 degrees Celsius or so, right around there is our average temperature. So we're getting pretty warm, or that's just the average. But if we look at those deviations from somewhere that's along the equator to somewhere that's kind of in the lower mid latitudes to somewhere like Churchill, up near the bay up there in Canada, those fluctuations are much more drastic. We go from negative 30 degrees Celsius, or right on the cusp of negative 30 and negative 24 degrees Celsius in January, to 12 to 16 or 12 to 18 degrees Celsius in June, or July, pardon me. Here we can see the mean monthly temperatures for Manaus versus Dallas-Fort Worth. We start to see that bump, right, to Churchill up in Manitoba. So we can see the influence of latitude on climate. So in which month does temperature decrease most rapidly with increasing latitude? It's a good question. I'll leave that for you to figure out. So in which month does temperature decrease most rapidly with increasing latitude? So think about that as we continue on. So the next control is elevation. So that makes sense, or should make sense. Temperature generally decreases with increasing elevation. So a quick aside before we really get into that. Elevation versus altitude, these are words we kind of throw around a lot. The term elevation is mainly used when referring to points on the Earth's surface. So like a mountain, the elevation, the top of the mountain, versus altitude, which is typically used for points above the surface, such as like an aircraft or a spacecraft or a drone, for example. Here we should remember this. This is our view of the troposphere, stratosphere, mesosphere, and thermosphere that we looked at when we were talking about our structure of the atmosphere videos way back in the first few weeks of class. So here we can see a pretty steep drop off in temperature going from the surface to the tropopause. Recall that at the tropopause, you kind of have a stop. These are very stable air mass, a decrease in lack of change in our thermal gradient. And then you see it increasing through the stratosphere. And then we have the stratopause, drops way down in temperature up to the mesopause, and then etc. So why? I guess the question is, and try to think about this as we move on to the next couple slides where I might give the answer here. What drives that difference? We see a really fast drop off in temperature as we go from 0 to about 11 kilometers in altitude. Well, elevation is a big driver. So here we can see a couple mountains, and what's at the top of those mountains? One is in Africa, the other, oh gosh, I can't remember where this picture is from. But as we look at them, we see they're snow-capped. So clearly, temperature is much colder up there. Why? Well, on average, about 50% of the sunlight arriving at the top of the atmosphere passes through the atmosphere and is absorbed at the ground. If we think back to kind of albedo and our Earth-Sun energy balances, 20% is absorbed by the gases, 30% is reflected back into space. So what we get is a warming of the ground, right? So the air in contact with the ground is warmer just above the ground. So as you get further and further away from the warm ground, the air is colder and colder. So this kind of explains why that air temperature decreases with increasing altitude within the troposphere. So, I mean, if we think about it, and we've talked about it before, cold air descends, warm air rises, right? Well, as you're kind of going up, you're getting away from the immediately warmed air particles and air masses within our atmosphere, our lower atmosphere. So you start to drop off very quick and you start to cool off very quick, if that makes sense. That's why you see snow-capped mountains, right? Because you're getting away from the majority of the land surface. And when you get away from the majority of that land surface, you're getting away from the moderating effect that that land surface has on heating the lower atmosphere. It's why we look at areas like the Tibetan Plateau, and we see that they are significantly colder than the air, or than the average temperatures around them in both January and in July. Same with the Andes, compared to areas like Lambarene and Nairobi, right? Lower in atmosphere in general, lower in elevation, not within a plateau or a mountain range. So here we can see Lambarene, Gabon, and Nairobi, Kenya. So we can see these are not nearly as impacted as, for example, a high alpine region would be. Moving into the next one, land-water thermal contrasts. So we've talked about and alluded to before the maritime effect. So near large bodies of water, surface air temperature is, generally speaking, warmer in winter, cooler in summer, compared to areas that aren't near a large body of water. Eau Claire, Wisconsin versus Astoria, Oregon, right? We don't have a moderating large body of water like they do along the Pacific coast. So we refer to that moderating effect as the maritime effect. In the absence of the maritime effect, we have continentality or the continental effect. So we have to think about how material, whether that be water or land, heats up. So land will heat up quicker and cool down quicker. Water heats up slower and cools down slower. So it has a more moderating effect on the proximal area to a large moderating body of water. Well, why? As I said, water has a much higher specific heat than land. So that quantity of energy, a unit mass of matter, must gain or lose for its temperature to go up or down. So it has a much higher, water has a much higher specific heat. The average specific heat, so we can look at dry land, is about 850 kilojoules per kilogram. Water, 4,200 kilojoules per kilogram. Water can mix. You have rotation within the water column. Land cannot. So it is preferentially heated along the top of that surface of land, where water, because of how fluids mix, can actually mix, and that thermal gradient can spread out more evenly. Water is transparent, so the rays of light can penetrate further in. Land is opaque. It can't. And then again, water can evaporate. So those phase changes and latent heat exchange can happen. Land, it doesn't happen. If we think of Astoria, Oregon, as we were talking about before, compared to St. Cloud, Minnesota, for example, we can see Astoria, pretty moderate. Doesn't really change much throughout the year. Whereas St. Cloud, we go from pretty frigid to pretty warm. Here are those mean monthly temperature graphs for Astoria and St. Cloud, right? We see a much bigger variation, a much bigger range in St. Cloud than we would in Astoria. Our fourth is ocean currents. We're going to dive, pun intended, a lot deeper into ocean currents a little bit later in our next week or so. And when we do, we're really going to learn about the effect that ocean currents have on impacting and driving climate. You've probably heard of the terms El Nino or La Nina or ENSO events, right? El Nino Southern Oscillation events, or the Pacific Decadal Oscillation. These larger scale, smaller scale, for example, like temporally, they span over years. There are multi-year to multi-decadal trends in things like ocean currents and climate that are driven by the way that ocean currents function and some things called gyres. So like these big ocean systems, if you will. So here we can see this. We've got, and you've seen this before, we've got the California current bringing kind of colder air down from the North Pacific. We've got the Gulf Stream and the North Atlantic Drift bringing warmer currents up the coast of America, or the North American continent, and kind of sending them up into towards Iceland area. We've got the Humboldt-Peru current bringing colder water up from the Antarctic Circle area. We've got the Canary current bringing kind of warmer currents descending down. We've got the Brazil current. So the Brazil current, we see a mixing between the Brazil current bringing warmer South equatorial waters down and the Benguela current bringing kind of colder stuff up the Cape of Africa. We see the Agulhas current also coming down between kind of Madagascar and South Africa, bringing some warmer descending currents from a little bit further up in the Indian Ocean area. We see the West Australia current bringing some colder water as it's been cycling through kind of the lower portion, South Seas area. We see the East Australia current, so kind of coming over within that broader Pacific South equatorial current zone, bring some warmer water down there along that east coast, and the Kuroshio current kind of spinning away up there in the North Pacific area down to the equator. So definitely know these ocean currents. It's going to come in handy. We'll talk about them and talk about ocean currents in general a little bit more in depth in the future weeks. But we can see the impact that places like Iquique and Vitoria, different sides of the continent, have based off of those current trends. And I say current as an ocean current trends. Here we see Vitoria, Brazil, and there we see Iquique. And we can see Iquique, which is along that colder ocean current, is generally speaking colder than it is in Vitoria, Brazil. Next, atmospheric circulation patterns. This is another one that we're going to dive into a lot more in depth in a future video, but we're going to touch on it here. So we look at things like prevailing winds, prevailing advection currents, how pressure systems set up and entrench within our atmosphere and across our planet. We can see areas again like Astoria and St. Cloud or Halifax. We can see how those vary. Again, we're not going to talk about it in too much depth today, but we can see that something is driving these bigger circulation trends across the continent, excuse me, and across the world. So we think about that as we go into kind of some of the next stuff. So prevailing vertical motions. So if we think about how warm and cold air masses interact, we think of kind of cold air descending, warm air rising, that circular kind of convective cell stuff. We think of things like cloud formation and wetter regions where those trends set up. These are bigger atmospheric trends versus areas where we're seeing drier air masses where condensation isn't occurring as much. And we see those as kind of our more arid regions. So Little Rock versus Abu Kamal. We see here a bit colder in Little Rock than it is in Abu Kamal, Syria. Or Verkhoyansk, for example. We see very large range, but there are atmospheric circulation patterns that are driving these changes. So we're going to talk about those in a future video. We're going to leave with this one here just to kind of watch at this trend in air temperatures from January through December. This is average based off of a 1971 to 2000 climate. We can see how it changes and how those kind of heated zones in the center fluctuate between the tropics, right? So as you're watching this, notice where some of the deviations are. We think about where those cold ocean climates are, or ocean currents are coming up. For example, the west coast of South America or the southwest coast of Africa versus some of the warmer currents on kind of the Gulf Coast of the United States or the east coast of Africa. Start thinking about how these relate to our broader atmospheric circulation patterns, to elevation. We see the plateau sticking out really, really well. We see the Andes sticking out well. We see kind of these bigger, broader mountain chains like the Alps and some of our larger mountain chains across the world sticking out. What drives temperature, and therefore what drives climate? That's what we're going to start to touch on now as we move forward. So I hope you enjoyed this video, and I look forward to talking to you more here in the future about current events, we'll say, ocean current events, and how these large-scale global patterns drive our climate and, by proxy, our weather. So have a great day, and I'll see you in the next video.